What you're doing in this assignment is you're finding net electric field strength at a particular location in space due to multiple sources. And to calculate electric field strength due to a point charge, you use E equals K Q over R squared. You can't get the direction out of that formula. You have to think about the direction and think about putting in a positive test charge to determine the direction. If you have multiple sources, then it just means that you have to calculate the electric field strength at the particular location. This one is midway between. So you would have some imaginary point. Well, it's not an imaginary point. It's a point in space. And you would calculate the electric field strength at that location due to the charge on the left. You would calculate the electric field strength at that point due to the charge on the right. You would then add the two electric field strengths, but you can't add them unless you know the directions. So when you calculate the electric field strength at the middle point in space here due to the charge on the left, since the charge on the left is a positive charge, the electric field strength at that point due to that charge is to the right, away from it, because an imaginary test charge would be repelled from that source. And the direction of the electric field at that point due to the negative charge to the right of it would also be to the right, because an imaginary positive test charge at that point would be attracted to that negative source, which means it would be towards the right. And you would add those two vectors together. I don't know if I had a chance to fix this or not, but in question 4 and 5, there's a word there that really shouldn't be there. It's the word other. Is it in yours? It's not. Okay, I removed it. That's good. Does anybody have any questions you would like me to go over from that? I think this stuff is a case of you know what you need to do, so if you're getting a wrong answer, you have to backtrack and retrace your steps and see if you can figure out where you made a mistake. All right. So you'll want to open up your handout to the next lesson, which is 2.5, I believe. It would be on page 27, and it deals with graphical analysis. In order to understand graphical analysis, well, I'll just say in general to begin with, when you design an experiment or when you investigate the real world scientifically, you're going to have experiments that involve variables, but you want to design an experiment that has only two variables. Okay? So if I want to know the relationship between how clean clothes get in terms of the temperature of the water I use, I would have to do a bunch of trials. I would have to wash some clothes with a low temperature, wash some clothes with a medium temperature, etc. But my two variables there would be cleanliness of the clothes. I don't quite know how you would measure that numerically, but that's a variable. It would be the responding variable. And the manipulated variable would be the temperature of the water I use. But when I do that experiment, I have to keep everything else constant. There might be other variables in that relationship, like how dirty the clothes are, right? But I want to keep that constant because it's not really possible to find out a particular relationship between two variables when you have a third one. I don't want to, have my cold water test with a t-shirt that has grass stains on it and my warm water test with a t-shirt that's covered in blood. I don't know where the blood came from, but I have to keep the dirtiness or the type of clothing the same. I would want to use the same cycle on the washer, meaning I don't want to go heavy duty on one and light on the other. I want to use the same washer. All of those things have to be kept the same. And then and only then can you see if there's a relationship between the variables. And the best way to visually see if there's a relationship between variables is to look at a graph, to plot a graph of the variables. So I love chicken wings, but my doctor says I'm eating too many chicken wings. It's bad for my heart, bad for my blood pressure, all that. So I try to cut back, and I only have chicken wings on Friday night. But I'm the furthest thing from a vegan or a vegetarian. But there's that part of my brain back here somewhere that makes me feel guilty. And whenever I eat chicken wings, I end up invariably having nightmares involving chickens. They're coming at me, they're pecking me, chasing me. And obviously this is fictional. I do love chicken wings, and I eat chicken wings every Friday, but I sleep like a baby, okay? However, imagine that I have this guilty conscience. And I'm a curious guy, so I decide to keep track over the course of, a few months what's going on. And I eat some chicken wings on Friday, and this is the manipulated variable. I look at the menu and I decide how many I'm going to order and how many I'm going to eat. And I wake up in a cold sweat and I put a mark on a piece of paper, and then I go back to sleep and I wake up again and I keep track of the nightmares. And what happens, of course, is there's some kind of relationship here. And again, this is fictional. It's just something that will help us remember things. And what I discover is that for the most part, this is a linear relationship. And I think you would agree that if there was a linear relationship in nature and you did an experiment, the data is not going to fall in a perfect line because there's experimental error. So think of this wobbliness of experimental error. Now, if I want to find out the relationship between all of these variables, I can draw a line connecting them, or a line, I guess, not connecting them, that's the wrong word, a line that is what we call the line of best fit. And I feel that this line accurately represents what's going on. And a line is our goal in any physics experiment. We want to get a straight line because the analysis of a straight line is very simple. In Math 10, you're taught that y is equal to mx plus b. So if I wanted to know the equation of this line, I would need to know the slope. So let's say I did that. I picked 2 points on the line. Notice, by the way, I pick 2 points on the line that are far away from each other, and I don't pick data points. You're not allowed to analyze the data by just using the numbers that are the data points. And the reason for that is if you could do that, why would you need a graph? Okay, you have to use points on the line. And when you find the slope, you want to choose points that are relatively far away from each other. Because you're going to have some error in reading these numbers to find your rise and your run. And if you pick 2 points that are really, really close together, imagine a tiny triangle right near the middle, that error is going to be a more significant percentage of your whole thing you're trying to measure. Okay? And let's say that I find the slope to be 0.25. And if you look at the units, it would be 0.25 nightmares per chicken wing, which means, kind of experimentally speaking, every time I eat 4 chicken wings, I'm going to have a nightmare. It's telling me something about the relationship between the variables. And let's say that I look on the graph and I see that the y-intercept is -1. Well, the y-intercept then would be -1 chicken wing. And that would mean that this is the equation. That I could, based on this data, come to a conclusion that the number of nightmares I have is going to be equal to 0.25 times the number of wings I eat minus 1. It's like I get a free nightmare. Or I get a free buy from a nightmare. Okay? I don't have that nightmare. So I can eat 4 chicken wings and still be okay. I go past 4, I start getting nightmares. Aside from the silliness of this, does this analysis make sense to you? You're taking data, you're seeing it falls in a straight line, you're finding the slope and the y-intercept, and you're building an equation. Okay, with that said, let's take a look at some examples dealing with physics. And the first example is this one. And I didn't teach any of you Physics 20, but this is a lab I do in Physics 20, and this is the actual analysis we do. In Physics 20, you're taught something called Hooke's Law. And Hooke's Law says that if you, among other things, if you take a spring and hang it, say, from the ceiling, and you put a mass on there, that mass produces a force of gravity that stretches the spring. And that force of gravity stretches the spring a certain amount from where it was. Hooke's Law says that the force you put on the spring is proportional to how much it stretches. Or how much you stretch the spring is proportional to the force. In fact, this is on your formula sheet. Now, I'm going to give you a different variation of it because on your formula sheet, there are no absolute value signs, and there's also a negative in front of the k, and I don't want to get into that because it's not relevant to our discussion. Do you remember F equals kx for a spring? Okay. I mean, just think about all that means is if I take a spring and I stretch it this much, I can feel some force pulling it back, but if I stretch it twice as much, I feel twice the force. That's all. So we do this experiment in Physics 20. In this case, the graph is given to you as part of this question. Sometimes it may not be, and we'll talk about what to do if it's not. So the graph is given. We can see there's a magnitude of displacement, x, 10 to the negative 2 meters. There's a magnitude of a force in 0.1 newtons. And the question is, what's the slope of the line of best fit? Show your work, and then relate the slope of the line of best fit to the spring constant to determine the spring constant. Now, let's do this. And you need to understand that this is an exam question. Although the physics content here is Physics 20, you could be asked to do this in a Physics 30 concept. And this is typically a numerical response question, so you can't be sloppy about doing it. You need to pick some points that you can read accurately. I'm going to pick, and you can pick your own points if you like, but I'm going to pick this point right here because it's right on what I call crosshairs or grid lines on the graph. I can read that very accurately, and I'm also going to pick, I want to pick another point I can read accurately, but I don't think it's a good idea to pick this point here because what I will gain in accuracy from reading that point will be lost because the triangle is too small, right? So I would probably pick this point here. And sooner or later, you're going to get to a problem where you cannot read 2 points precisely. And what I would say to you is you read them as accurately as you can. So we would construct, and I am going to hand out rulers today. I don't know that you really need rulers. And trust me that your triangle needs to be large. If you don't, the diploma exam is ruthless about the accuracy of graphical determinations. You're welcome. There you go. So, as I said, I don't know that you need a ruler here, but some people like a ruler so they can see the triangle that we're talking about. So I just use a dotted line. It doesn't have to be a dotted line. My dotted line is quite thick, but that's only because I want you to be able to see it. These red arrows here are just so that you could see what points I was referring to. And now I'm going to read the rise. The rise is, well, this is 33. This is 8. It's times 10 to the negative 1. So that would be 33 times 10 to the negative 1 is 3.3 minus 8 times 10 to the negative 1 is 0.8. And this is newtons. So I get 2.5 newtons. One of the biggest mistakes that you can make in any type of graphical analysis on an exam is not paying attention to the scientific notation, if there is any, for the units. We're on page 27 of the handout I gave you yesterday. So the rise is 2.5 newtons on my graph. I mean, if you chose different points, you're going to get a different rise. My run, let's see, this is 10 to the negative 2. So what is my run? My run is 14 times 10 to the negative 2. I'll do this slightly differently. 14 minus this is, ooh, this is a tricky scale here, isn't it? Well, let me explain it first, though, please. So the first number on the right was easy to read, but this is a little bit more difficult. And you encounter this scale quite often, where you have from here to here, this distance is 2, but it's equal to 5 squares. And this is just the way my brain works. I don't know where I picked it up. I don't think of 2, I just think of 20, because I can divide 20 by 5 easier in my head. So 20 divided by 5 is 4. So if this were 20 being 5 squares, it would be 4, 8, 12, 16, 20. But it's 2, which means it's 0.4, 0.8, 0.6, 0.12, 0.16, 2. So each square on the bottom is 0.4. So when you take a look at this point, and the point that we're interested in is right here, let me adjust that now, it's right here. We're at 2, 2.4, 2.8. So it's 14 minus 2.8, and I said I would just enter this a different way on the board, times 10 to the negative 2 meters. You're allowed to do that. We could multiply each of them by 10 to the negative 2 and then subtract, or we could just subtract. So when I do that, sorry, I lost my page there. I think I must have deleted it. There we go. When we do that, you get, I believe, 11.2 times 10 to the negative 2. Am I right? Okay, starting to see some people say yes. So my run is 11.2 times 10 to the negative 8. And that means that my slope, we use the symbol m for slope, which is rise over run, will be equal to my rise, which was 2.5 newtons, over my run, which was 11.2 times 10 to the negative 2 meters. So I'm going to stop there before we divide that. Does anybody have any questions? Or are we in agreement on those numbers using the points I've chosen? Okay, good. So what do I get for the slope? Well, using those points, I get 22.3. And I don't think we really want to get into a large discussion here about significant figures from a graph. Very often we just go with 2 significant digits from a graph because there's always some difficulty in reading to more decimal places. But I'm just going to go with 22.3 anyway. Okay? So the slope is 22.3 newtons per meter. And now we are asked, we've determined the slope. We've determined the slope. Now we are asked to determine the spring constant from that. And I know that most of you know that the slope is a spring constant. But trust me that the graphical analyses are going to be getting more and more complicated. So I want to explain to you in a very general sense what's going on here. We have this formula on your formula sheet, and I'm not going to worry about vector symbols or absolute value or anything like that. And it's Fs, the force on the spring, equals Kx. And this is a physics relationship, right? It's describing physical quantities. But mathematically, when we look at this line, it's a straight line, which means that it has to follow the rule of y equals mx plus b. This is very tricky and subtle. I put the plus b in a very faded, hard to see ink because there shouldn't be a B here, right? In theory, if you don't apply a force to the spring, it will not stretch. I think that's reasonable. But this is an experiment. And if I were to extend this line, this line does not go through the origin. So why not? Okay, there are two reasons, and this is where we're getting into the physics 30 aspect of things. One is that for some reason, all of your measured forces were significantly higher because of experimental error. Maybe the spring scale that you're using to measure the forces, I don't know how much you worked with spring scales last year in Physics 20, but they have a little metal guide in there that with a pointer on it, but that guide moves around. You can move the guide. So maybe the person who collected this data had the guide with the increments on it slipped a little bit right at the beginning of the experiment, and when there was nothing attached to it, it was actually showing a force. That could be a physical reason. It could as well be, other than a physical reason that it doesn't go through the origin, there could be just some error in your experiment. I mean, that's a physical reason. That's a consistent error. But it could just be that you drew the line a little bit weird. There are all kinds of reasons why, even though the physics equation should not go through the origin, the actual equation does. Okay, so we're going to just make a note here that this is the math equation. And what we want to do is compare them. So our physics equation says that we have force, but when you look at your graph, force is plotted on the y-axis, so the force is the y. In our physics equation, we have, and this is why I chose this example to start with, we have x, which is a displacement of the spring from its original position, and that's plotted on the horizontal axis. I didn't mean to do that. We have the displacement of the mass, and that's plotted on the horizontal axis. Well, just by way of comparison, what that means is that this has to be the slope. And it has nothing to do with any y-intercept that may or may not be there. Now, I can see you're struggling here to how would you write that down if you don't have colors? Well, you could do this. So if you have a written response problem that you're working on, or you're doing a quiz or something where I'm asking you to show your work, I guess that would be a good way to communicate that you're comparing y to the force, x to x, and your slope then becomes the spring constant. So the conclusion out of this is that k equals the slope, but we've determined the slope was, my brain wants to say 22.3. Was that what we got? Okay. And that's the spring constant. We're on page 27. Good morning. Before we move on, any questions with that analysis, that comparison? And as I said, it's going to get trickier, a lot trickier than this. All right, now, if a mass of 120 grams was placed on the spring, what would the predicted displacement be? So first of all, this spring is hanging vertically. I don't know if I've said that in the question, but that's my intention. So if this is 0.120 kilograms, which is what it is, the force on the spring is the force of gravity, which is mg. So let's calculate that. What is this downward force acting on that spring? Well, it's the force of gravity, which is m times g, which is 0.12 kilograms times 9.81 newtons per kilogram which is going to be about 1.2 newtons. Let's just find out. 0.12 times 9.81 is 1.1772 newtons. So what we are dealing with here in this question, everybody, is if the force on the spring is 1.1772 newtons, what's its displacement? Okay. And here's where you will get it wrong if all you do is rely on the formula and not on the experiment. Because if you rely on the formula, so just hang back on writing anything just yet. If you say, well, F equals Kx, and I know F, and I put it in there and I divide by my K, which I know, right? Let's even try that. You're not writing this down just yet. But let's try, let's see what would happen if you had 1.1772 equals K, which is, this is newtons, K, which is 22.3 newtons per meter, times X, and I solve that for X. I'm going to take that force divided by that spring constant, right? And it's going to be wrong, or it could potentially be wrong. And I'm not talking about the fact that the slope wasn't exactly 22.3. Let's just use 22.3. We get this. So you get 5.3 times 10 to the negative 2 meters. Okay? Well, let's take a look at the graph. We had a force of 1.1772 newtons. So where would that be? Well, these are times 10 to the negative 1. So this is 2 newtons right here. This is 1 newton. This is 1.5. So 1.7, well, 1.75 would be here, wouldn't it? This would be, what are we dealing with? 5 divided by 4. This is 16.25, or 1.625. This is plus another 1.25. That would be approximately, what's 2/3 of 5? This is, my brain just hit a roadblock. 20 divided by 5. Sorry, 5. Oh, each of those is just 1. What am I thinking, right? 15, 16, 17, 18, 19, 20. Okay. So we are looking for 1.1772. Let's call it 1.2, which would be here. Are you in agreement? If we read the graph, what do we get here? We get that number, don't we? Look what we got when we used the equation. When you use the equation, I got to do it again. 1.1772 divided by 22.3. When you use the equation, you got over 5 centimeters. But it's not over 5 centimeters. You can see it's less than 5. What's going on here? Why is the equation not working?
The B value?
Right, there's a B value. And you can say all you want that there shouldn't be a B value. There shouldn't. But the experiment shows there is. So if you're asked for the experimental result of using a particular force, you have to use the experimental data, which includes that B value. So now when we solve this problem, this is the point I want to make, you have to use this. You have to go to your graph and read the B value off of the graph. Because, look, I don't care why all of the data is shifted up when it shouldn't be. It is. So we have to use that fact when we do this. So I'm going to read this, and I can see it's just a smidgen less than 2 squares on mine. Would you agree? I'm going to estimate and say it's about 1.9 times 10 to the negative 1. Can you live with that? Okay. That means that our actual equation of the data is y equals the slope, which was 22.3 times x plus 0.19. Because that's the y-intercept, 0.19 newtons. Don't forget, it's 2 on the axis, but it's times 10 to the negative 1, which gives us that. Now what happens, of course, when we put in the numbers, we have 0.11772. Was that number right? Okay. Equals 22.3 times x plus 0.19. You can see mathematically what happens. No, it's 1 point. Okay, you can see mathematically what happens is that that number that we divided by 22.3 earlier is going to be reduced a little bit first, and that will give us an accurate answer. So solve that equation for me, please. You're going to take that force minus 0.19 and then divide by 22.3. Sorry for my fumbling around trying to read that axis. I don't know why it was so difficult for me. I have to subtract the 0.19 first. Then I'm going to divide that by 22.3. So you're looking at about 4.4 centimeters. And in fact, when you take a look at doing this from the graph, it's not quite 4.4. It's probably 4.35 or right around there, but it's closer. And by the way, you would never want to try to answer these questions by just reading the numbers from the graph. Okay? So if there is a y-intercept, you have to use it in your analysis, even though there maybe shouldn't be a y-intercept. And 4, if the displacement of the mass is measured to be 50 centimeters, what force would be produced? Well, we have this formula, force equals 22.3 times x plus 0.19. Well, you're just going to put this in for x. But the graph has it in meters, right? So we're going to have to put in 0.5 meters. The graph is all standard units. So the force will be 22.3 times 0.5 meters plus 0.19. And if you want, this is newtons per meter. This is meters. This is newtons. You can see how you're going to get newtons out of this. So we need to take 22.3, multiply by 0.5, and get 11.15, add 0.19, and get 11.34. Am I right? Okay, so it's 11.34, and we would probably just record 11.3 newtons. Now, everything I've done so far in the last 20, 25 minutes or so is not physics 30 related. It's in terms of content, but it's related in terms of the idea of a graphical analysis. Let's move on now, and let's take a look at a situation that is a physics 30 situation. In an experiment designed to determine the value of Coulomb's constant, students use an electric probe. I'm oversimplifying things here. But you can buy electric probes that measure electric field strength. We don't have them in this lab. At a distance of 75 centimeters away from different source charges. By the way, I don't mean a whole bunch at the same time. What I mean is they put a source charge right here at my fingertips. 75 centimeters away, they read the electric field strength, they write it down. They change the source charge, they repeat it. So they're collecting source charge and electric field strength for data. Before I get to the graph, we have a manipulated variable, which is the source charge. If this is a math class, we tend to call it independent variable, but it goes on the horizontal axis. The responding variable, or in math, what we call the dependent variable, is the electric field strength. What are controlled variables here? What are some variables, or I don't really like the word variable here, but we use it anyway. What are some things in this experiment that you have to keep constant? Or that are kept constant? Yep.
Is it a spring constant?
Well, there's no spring constant that connects these.
Oh, right.
But I have a feeling I know why your brain went there. there is going to be something equivalent to the spring constant that is being kept constant. But there's more than one thing. Does anybody know? Yep. The distance. R. This is the equivalent of me trying to find the relationship between temperature of wash water and the cleanliness of clothes. I want to keep the wash cycle the same, or I want to keep the dirtiness to begin with the same. There's one other one that's very important, and you may not get it right away because it's not something that you really have control over, but it is fixed in this experiment. Anybody know? Okay, what's the relationship between the electric field strength and the charge? Go to your formula sheet. What's the relationship between electric field strength and the source charge? We were just working with this right at the beginning of class when we went over yesterday's stuff. E equals kq over r squared, right? So in that formula, look at that formula. E, electric field strength magnitude, equals kq over r squared. This is my y. This is my x. R is fixed, but so is k. K is also a controlled variable, and that's why I don't, Alberta Ed uses that phrase here. I don't like it because k is not actually a variable. K is a constant in every experiment. You're keeping r to be a constant here by physically limiting the distance and saying, I want to use 75 centimeters. But you're also keeping k constant because the universe is playing nicely. Okay? So the second controlled variable is Coulomb's constant. And here's what's going to happen in any graphical analysis problem. You're going to have two variables that create a graph, and all of the other constants are going to be connected to either the slope or the y-intercept of the graph. And one of those other things that are controlled, which is connected to the slope or the y-intercept, will be the thing you're trying to find. And this question says, the students are trying to determine the value of Coulomb's constant. So now let's take a look at the graph. There's the graph. It's a straight line. Why is it a straight line? Well, the reason it's a straight line is because y equals mx plus b is the equation of any straight line. And this formula, everybody, that I have written right here, if I take this formula and I nudge, do that again too, and I nudge that q over here, then I have y equals constant times x. The slope is going to be k over r squared. So the reason why you get a straight line is because electric field strength is equal to k over r squared times the charge. And y is equal to the constant, which is the slope, times x. You know, again, plus b. You can choose to indicate what I'm telling you in any way you like. That's plotted on the y-axis. This is plotted on the x-axis. And what that tells us is that the slope of this line is equal to k over r squared. It's not just equal to a spring constant. And by the way, there's a k in this formula, right? That k in this formula is Coulomb's constant. The k in the formula of the first warm-up graph was the spring constant. Now, there shouldn't be a y-intercept in this physics equation. Will this graph have a y-intercept? Definitely. You can see it's not going to go through the origin. So what we're asked to do in the first one is determine the slope of the line and relate it to Coulomb's constant and calculate Coulomb's constant. So I'm going to give everybody a minute here to pick a couple of points on the graph. It doesn't have to be perfect. Oh, there's one. If you can't find 2 points that you can read really accurately, that's fine. But find a couple of points that you can read reasonably well. I'm choosing these points. I'm going to give everybody a minute or two to find the slope of that line. We are dealing with vertically the same kind of scale we had horizontally last time. Every square, I believe, is 0.4. 0.4, 0.8, 1.2, 1.62, etc. Don't forget that your rise is times 10 to the negative 4 newtons per coulomb, and your run is 10 to the negative 6 coulombs. Across the horizontal axis, each square is 0.2. So for example, 6, 6.2, 6.4, 6.6, 6.87. I just want to step back and make sure that I've read my numbers right. 10.4, 10.6, 11.2, 11.6, 3.2. On the bottom, I have 6.6 minus 1.2. The top is 10 to the negative 4. The bottom is 10 to the negative 6. How many of you are getting a slope in the neighborhood of about 1.6 times 10 to the 10? Okay, and you should. When you look at the units, and you know from having me as a physics teacher for only a few weeks that I'm not a big fan of units in doing your everyday work, in learning and teaching, but I think they're important in graphical analysis. We're going to have newtons per coulomb squared. That's the slope. Now, how are we going to use that to find Coulomb's constant? The answer is what's highlighted in yellow. That number, along with those units, is the slope. And that has to be equal to Coulomb's constant, the experimental value of Coulomb's constant, divided by r squared. So if the slope equals k over r squared, and our slope is 1.6 times 10 to the 10 Newton per Coulomb squared, that has to equal the experimental value of Coulomb's constant over that distance that we kept fixed, quantity squared. So if we multiply our slope, just looking at this purely mathematically, look at this equation. Forget about the units. You have a number equals an unknown over a number. You have to multiply that 1.6 times 10 to the negative 10 by the 0.75 squared. So you're getting 9.1 times 10 to the 9 I didn't count the decimals, but I'm pretty sure it's going to say it's going to be 10 to the 9. And the units will be the Newton per Coulomb squared that we had times the meters squared. And that's not bad for any kind of high school experiment, certainly in finding Coulomb's law. You're less than about 10%. Any questions with that one? If I seem like I'm going extra slow with this, it's because I know that it requires a lot of thought for some students. I think, and it's a fault of mine just here as a teacher, I think this comparison that I've got is just obvious. You compare y to y, x to x, and everything else falls into place. But some students really struggle with it. Okay. Let's take a look at the next question. What would the predicted electric field strength be if that were the source charge? So we have this formula, E equals kq over r squared. Okay, first of all, I'm not allowed to calculate this by putting 12 microcoulombs in for Q, 0.75 meters in for R, and 8.99 times 10 to the 9 in for K, because I want an experimental prediction. I can't use the number on the formula sheet. I have to use the experimental value of K. But even if I did that, I will not get the right answer to this question. I'll get burned on an exam. Why, even if I put in the experimental value of K, why will this not give me the correct answer?
B value.
There's a B value. There's a y-intercept. There really ought not to be a B value. But for whatever reason, maybe the probe is calibrated wrong. All of the data has been, in this case, shifted up. Sometimes it's shifted down. Okay. So we have to include that. And that means we have to go back to the graph, use our ruler to extend the line, and read the y-intercept so that we can use it in our calculation. And you know what I'm getting at just before you do that? What I'm getting at is when you're asked these questions where you have maybe a Q and you're trying to find F or E, or in general, when you have an X and you're trying to find Y, what I'm telling you is you don't use this equation. Use this equation because it's what's showing you the information. You have to use the y equals mx plus b. So I'm sure in all that blabbing you probably extended your line already. Let me take a crack at it up here. It's not bad. Now I might be a little off, but 0.41, that would be 1.2, 1.1. I would probably on mine say 1.105. How many of yours is pretty much, pardon me, no I wouldn't. I would probably say about 0.905. How many of yours is right at 0.8? So are yours all a little bit higher than 0.8? Oh, okay. So can we go 0.9? I mean, we're not landing people on Mars here. So you have to follow the y equals mx plus b formula when we do the substitution. You put y equals, the slope is 1.6 times 10 to the 10. X is the 12 times 10 to the negative 6, and then your y-intercept is what we recorded. So what do we get? 1.6 times 10 to the 10 times the 12 times 10 to the negative 6. So this is what you would get if you did not include the y-intercept. If you thought, well, physics says there shouldn't be a y-intercept, so I'll just do that. And that, by the way, Annalie and everybody, that's what you would get if you took the experimental value of Coulomb's constant times your Q that you're given over the 0.75 squared. But if you just take the slope, you don't have to worry about that over r squared. However, we still have to add the 0.9 times 10 to the 4. So that's the correct answer. And thank you for the correction. It's tricky stuff. Let's try example 2. And this is where we're going to end up. And we're going to spend 2 days on this. So I want to power through and at least set this up. And it might be the case that your assignment is just to finish this example. Or it might be to do 1 question or 2 questions for Monday. In an experiment designed to determine Coulomb's constant, you take 2 charged objects. Those are fixed charges. We're not going to change them throughout the experiment. And you're going to put them a certain distance apart and measure the force. And then you're going to change the distance and measure the force. Unfortunately, your variables of electric force and R are not linearly related. Now, I know you've got a graph in front of you, but before you get to the graph, if I were to plot this graph it would look like that. That's what an inverse relationship looks like. As R gets bigger, the force drops off. It's not a straight line. So I want to explain to you why we get a straight line if you plot 1 over R squared here. So what does this mean? It means that maybe, everybody, you measure R to be in the experiment 1.2 meters. If you take 1 divided by 1.2 squared, do that for me. What's 1 divided by 1.2 squared? You're going to get 0.694. And that becomes your x-coordinate. That's what's plotted on the x-axis. If it was 0.9 meters, well, you'd take 1 divided by 0.9 squared. And you'd put 1.1 there. I didn't square it. Thank you. You'd get 1.23. But why do you get a straight line when you do that? The reason is a straight line by the way, there will come a time in this course where we will have a y-intercept because we're supposed to have a y-intercept. Not because maybe there's an error. The reason why that works is if you take Coulomb's law, and you say to yourself, well, the k is constant in this experiment, the q is constant, the q is constant, the variable is this r squared on the bottom. If you move that r squared over here and write it as 1 over r squared, then you can do your comparison of y equals mx. The blue is your y, the green is your x. That means your slope in this situation is that. But you're not going to get a straight line unless your x is 1 over r squared. Because Coulomb's law says the force equals these constants, not times r squared, but times 1 over r squared. So in order to get a straight line, you have to plot 1 over r squared. Am I right in saying this class ends at about 5 after 10? Roughly? Okay. So that's why you get a straight line, and the slope is equal to kqq. So in this particular question, if it says determine the slope and relate it to Coulomb's constant, well, we've already related it to Coulomb's constant. The slope is related to Coulomb's constant this way. Slope equals Coulomb's constant times the product of the charges. So how can we find Coulomb's constant? Find the slope and divide it by those 2 charges, and that will be Coulomb's constant. Now, given that I don't think I really want to assign a lot of homework, let me show you how you can determine the slope along with the y-intercept on your calculator without doing anything on paper. Put up your hand if in any math class or physics or science class a teacher has ever showed you a linear regression on your calculator. Put up your hand if any teacher has shown you how to enter data into a calculator so you can see the plot on the screen. Maybe in Math 20? Okay. Well, if you have, we're going to do the same thing, but we don't even need to see the plot. The plot is right in front of us. So here's what you're going to do. Follow along on your graphing calculator. You're going to hit the Stat key, which is right under the Delete key, just by your 4 arrows. And then you're going to hit Enter, and you're going to see lists. So does everybody have an L1 and an L2? In other words, put up your hand if you're missing L1 or L2. Like at the top, you don't see an L1 and an L2. Okay. How many of you have numbers in there already? Nobody, because you haven't been using this. If you ever have these numbers, these are called your lists, and you want to clear your lists, go to where you would go to clear your calculator memory, which is second plus, and you have an option that says Clear All Lists. And if I do that, and then I go back to Stat Edit, I can see my lists are empty. Now, what I'm going to do is enter my X data in L1 and my Y in L2. And then I'm going to tell my calculator to do what's called a linear regression. It's going to calculate the equation of the line of best fit. It's going to do the work for me. Since it's a straight line, I really don't need to enter a lot of data. In fact, I can just enter, I believe, 2 data points. So I would enter this point here, and I would enter this point here. So what is this x coordinate? 0.4, 0.8, 1.2, 1.2. The units happen to be over meters squared, but it's 1.2. That's my x coordinate of this point. I go 1.2 and I hit enter, and now I'm going to enter my x coordinate of this point, 14. I'm going to go over here. These are ordered pairs, so when I put 1.2 in L1, I have to line it up horizontally with whatever the y coordinate is for that point. And that is 0.2, 0.4, 0.6, 0.8 times 10 to the negative 3. And then I want to look at this. Well, that's 6.2, 6.4, 6.6, 6.8 times 10 to the negative 3. I want to prepare you for post-secondary, and I want to, give you the skills necessary. But at the same time, I know that all of your exams, including the diploma exam, are multiple choice numerical response. If you want to know the slope and the y-intercept, this is the quickest way to do it. So I've loaded in the information. Now I have to tell my calculator, find the equation of the line of best fit. And that's going to be the equation of the line that goes through those 2 points. And I do that by quitting out of here to my home screen, going back to my stat menu, and then going over to the calculate submenu. And there is something called linreg, which means linear regression. And my calculator is going to go to all the data I have in L1 and L2. It's going to treat L1 as x and L2 as y. And it's going to calculate the line that best represents a linear pattern, which is going to be a straight line through it. Now, if you have a calculator that's fancier than mine, then after I choose this, you're going to have to scroll through a bunch of things. Are you with me on that? To confirm that L1 is x and L2 is y and all that stuff. Here, I don't have to do that. My calculator, it's embedded in there. The default is L1 is x. When I hit enter, it grinds away for a second, and it gives me that answer. It tells me the equation of the line.
If we have the list, do we have to put like X and then Y in here?
Give me a second so that I can refer to it up here. What do I want? I want a new one. I want... It's weird. There it is. Ugh. Okay, just help me out here. Can you give me the X's?
1.2?
Okay, and 14?
Yeah.
Okay. And the Y's? Who's speaking? Louder?
0.8 times 10 to the negative 3.
Thank you. And?
6.8 times 10 to the negative 3.
So we're done over here on that calculator. Over here, you would go stat, calc, lin, reg, and this is what we're talking about. You see this. As long as nobody has messed with stuff, this is what we want. You really don't need to do anything else here. You just kind of go enter, enter, enter. There's some other options that we could deal with, but it's unimportant. And you get the same number, right? I mean, the underlying programming here is the same. So what does that mean? It means that the equation of the line of best fit here, the equation of the line of best fit is y equals the slope. Now, my calculator uses a instead of m, but that shouldn't matter. 4.6875 times 10 to the negative 4 times 10 to the negative 4 times x plus the y-intercept of 2.375 times 10 to the negative 4. I mean, you know, everybody, that really takes the guesswork out of reading data points. For rise and run, your calculator does the subtraction. We don't have to worry about extending the line and trying to figure out what that y-intercept is. It's right there. Now, just before we go on here, you need to, realize something. Y is in newtons. This is in newtons. Your slope, if you look at the graph, is newtons divided by the reciprocal of meters squared. It's newtons divided by the reciprocal of meters squared, which is newtons times meters squared. So this is in Newton meters squared. The whole thing times 10 to the negative 4 is. This is x, and it has units of 1 over meters squared. That certainly explains why when you multiply these two things, you'll get newtons. And this is newtons as well. And I'm going to end this by saying the formula in physics that's supposed to connect everything here is that. So again, and some people will see this more immediately than others, this is equal to KQQ. Our x is 1 over r squared, and the y-intercept is this many newtons. And I think what I'm going to say to everybody is, I want you to finish this example. This example doesn't ask you to find the force if the distance was a particular value. It doesn't ask you to do the opposite. All it asks you to do is find the experimental value of Coulomb's constant. And then I think what we're going to do Monday is do a quick review of all of this, and I know it's a lot to take in. And then we'll complete all of the assignment on Monday in class.